Hello, welcome back to MEC 416/816 Engineering Acoustics. In this video, we are going to go through what is known as the velocity potential. So one method to simplify the analysis of a vectorial differential equation is to derive that solution from what is known as a scalar potential. And in acoustics, we will use what is known as the velocity potential to do this. So in that regard, we have our fluid particle velocity u, and we can say that u, which is a vector here, is equal to minus del, that del operator again, acting on some scalar quantity, capital phi. And just want to note here that u is equal to some quantity u1 in the x1 direction plus quantity u2 in the x2 direction plus u3 in the x3 direction. And you can think of x1, x2, x3. These could be x, y, z in a standard Cartesian, or they could be some other kind of coordinate system. It all depends on what we're looking at. And so here we have that this fluid particle velocity is equal to the negative of the del operator acting on a scalar. And here the minus sign is just a matter of convention. So in the case of a one-dimensional fluid particle velocity, that's where we only have the u1 component, we can write here that this phi variable, that velocity potential, is equal to the negative of the integral of u1 times dx1 plus some constant. So in a 1D case, you can do that and you don't lose anything. However, when you go to 3 dimensions, if you try to do this integration as shown above, I'm sorry, not this integration, by introducing a velocity potential in a 3D case, we end up reducing the generality of the solution. And specifically what we can show is that if we take the partial of u1 over the partial of x2 minus the partial u2 over partial x1, we can show that this is equal to partial squared phi over partial x2 partial x1 minus partial squared phi over partial x1 times partial x2, and that is going to be equal to 0. What this means is, well, actually, if we do this for the x1, x and 3, and then x2 and x3, we'll get similar results. And what this really then leads to is that we get del crossed with u is equal to minus del crossed with del operating on phi, and that must be equal to 0. And this is known as Stokes' theorem. And what this means is that when we introduce a velocity potential, we end up with having rotationless solutions. That means that there can be no rotation in the solutions that we get. Fortunately, for acoustic motions, these are always going to be rotationless, even in the cases where the viscosity is non-negligible. And so what that means is that the introduction of a velocity potential is actually a good approach for what we're studying here. From there, we can introduce that velocity potential into the Euler's equation. Doing so results in the following. We get del, let me rewrite my del here, del p, del still a vector, is equal to minus rho 0 partial u over partial t. This is then equal to minus rho 0 partial over partial t acting on del phi. We can switch the order of the del and that partial derivative, and we'll get minus rho 0 times del times partial phi over partial t. And then integrating with respect to time, we'll get that. Sorry, integrating with respect to space in this case, we can find that the acoustic pressure P is equal to rho 0 times partial phi over partial t plus some constant. So if we know the velocity potential, we can now use that and find the acoustic pressure. And so thus all the velocity in all three components and the pressure can be derived from that velocity potential. If we now go ahead and substitute in equation 27 into the linear acoustic wave equation, and then integrate with respect to time and dropping the constant, we will end up with the following, that del squared phi is equal to 1 over c squared times partial squared phi over partial t squared. And so thus we find that the velocity potential itself satisfies the linear acoustic wave equation. Now, unfortunately, if you were trying to find some kind of physical interpretation for what the velocity potential is, there unfortunately is not a physical interpretation, and you can study that and try to create a physical meaning, and what you'll end up finding is that one explanation contradicts another explanation, and really there's just no physical meaning to the velocity potential, which in my opinion can be kind of unsatisfying at times. But this is a very useful and important tool, and is used all over acoustics. Okay, in the next video we are going to go through and study plane sound waves. Thank you.